So it's 7 o'clock, so let's go ahead and get started. Thank you so much for coming out to our Sky Talk this month. Dr. Troland will be our speaker. The weather looks good, so there will be a viewing opportunity after this, and will be open for the eclipse. So I'll give you more detailed timings for that once the talk is done. But otherwise, our speaker this month is Dr. Troland, so he can go ahead and get started.
Well, thank you, Erica. It's a pleasure to be here. I've been here at the University of Kentucky now for over 40 years, and I always enjoy talking about astronomy. Now, it's nice to see all of you who have come tonight. Glad to have you here, and we have perhaps some people listening in from afar on this topic. That's one of great interest. I was thinking that the motivation of this talk is the asteroid, which by some calculations was a probable strike on the Earth in 2032. If the probability of that strike was still very high, we'd probably have even more people here concerned about whether their life should continue, whether they should make Christmas plans, for example, because the near passage, hopefully, of this asteroid past the Earth will be on the 22nd of December in 2032. So if you really felt that this asteroid strike was likely, you might not want to bother to make Christmas plans for 2032, but I think you can go ahead and do that. Anyway, the fact that the chances of this impact are rather small might have reduced the interest of some people who otherwise would have been here, but I'm very happy to have those of you who are here. So the talk today will be on the topic of asteroids in general. And as always, of course, there's some slight problem here in the sense that the slide doesn't seem to change. Perhaps Erica can help me out somehow in that regard.
Try now.
Perfect. Okay, very nice. So the topic today, Wham, Bam, Earth in a jam. Now you have to wait towards the end of the talk to find out the answer of whether the Earth is in a jam or not. Don't worry too much about it. I don't want you to spend this whole talk too concerned, but the moon might be in a jam. We'll get to that a little bit later. Asteroids. Why do I show you this picture? This picture I took just yesterday out a window on the third floor of this building, looking out towards the back where there's a construction site. And there's a lot of mess around that construction site. But the thing is, as you know, once this construction project is completed, the mess will be cleaned up. It'll all look nice and smooth and clean. Now, another example of a construction site is shown here by this artistic illustration. The solar system was formed. The solar system was formed under construction 4.5 billion years ago. And so in those early days, there were a lot of bits and pieces still flying around. In fact, there still are some today. But you see, unlike construction sites here on Earth, such as the one right across the way from this building, construction sites in the solar system, in the universe at large, are not cleaned up. And so we have a lot of, I like to think of it as construction debris still floating around in the solar system, even after 4.5 billion years, because that's when we think the solar system formed. The solar system formed at that time out of a swirling disk of gas and dust, and towards the center of that disk, the majority of the mass accumulated to produce the sun, and in other locations in that disk, material gathered together, little bits and pieces sticking together, those bits and pieces sticking together more, creating bigger and bigger things, and a lot of collisions going on, and a lot of accumulation of material, eventually leading to a certain number of planets. But a lot of the stuff was not swept up. The construction debris of the solar system is still with us. And asteroids are part of that construction debris. We still have to live with them. Now, there are far fewer of these things flying around now than there were billions of years ago, but there still is construction debris. There still is construction debris in our solar system, and occasionally that construction debris can pose a problem. So asteroids are part of that problem. So what is an asteroid? Many of you in this group, I'm sure, know. But an asteroid, as you see here, is sort of it's the shattered remnant of a building block to the solar system 4.5 billion years ago. We don't understand entirely the details of how the solar system formed, but as I said a moment ago, in general, what happened is little bits and pieces stuck together, creating bigger pieces and bits and so forth. And some of these objects grew to be what we today call planetesimals, even though none of those are still around. The planetesimals, in some cases, grew into the planets that we have today. In other cases, some of those planetesimals just smashed into each other and created a lot more debris. And so asteroids that we have orbiting around the sun today are bits and pieces of that debris left over from the construction of the solar system 4.5 billion years ago. Different asteroids, as you might imagine, just like different pieces of construction debris across the way and from this building, different asteroids are made of different materials. Some are very rich in carbon, some are very rich in metals, particularly iron, and some are what are called stony asteroids, meaning that they're made up of silicate type materials predominantly. There's another type of object that's running around in the solar system as well, which in some ways is quite similar to an asteroid. It's called a comet nucleus. A comet nucleus is also a bit of construction debris. If a comet nucleus, which in the case of a comet nucleus is rich in various ices like water ice, ammonia ice, carbon monoxide ice, if a comet nucleus gets close enough to the sun, and most don't, but if it does, it can create a cometary tail. And many of you perhaps have seen comets. All of you have seen certainly pictures of them. Actually, asteroids and cometary nuclei are probably just different sides of the same coin. There's a whole spectrum of different properties of these smaller objects orbiting around the sun. And the asteroids tend to be more metallic, more stony, more rock-like. The cometary nuclei tend to be more icy, but with rocks mixed in. It's not clear that there's a clean distinction between asteroids and comet nuclei. And so in modern times, according to the International Astronomical Union, which is the international organization of astronomers, these two types of objects, asteroids and cometary nuclei, both bits of construction debris orbiting around the sun for billions of years, these two types of objects are lumped together into something called small solar system bodies. Certainly a very evocative, if not a particularly poetic name. So how would you find an asteroid? The problem with finding asteroids is that they're pretty small. By small, I mean a few hundred miles across at the very largest, and most are much, much smaller than that. It's very difficult to find an asteroid. And that's why the first asteroids were only discovered in the early 19th century, long after the telescope had been invented. And it really wasn't until the late 19th century, moving into the early 20th century, that a fair number of asteroids were discovered, because in order to discover an asteroid, by far the best way to do this is to use photography, either old film photography in the days of yore, or today electronic photography. So here is a picture now. Here is a picture that you see on the screen of a bunch of stars. Each star is represented by a little dot. And the arrow there, the yellow arrow, points to one of those dots. It looks no different from any of the other dots. That dot that the arrow designates, that dot is an asteroid. And all the other dots are stars that are thousands, if not tens of thousands of times more distant. So how can we tell that that little dot there at the end of the arrow is an asteroid in our solar system, and all those other dots are distant stars far, far, far away from our solar system? How could we tell? Well, the answer is quite straightforward, because you see, asteroids change their position over time, over hours, over days, over weeks, relative to the background of fixed, very distant stars. So now, in order to tell that that object there, pointed out by the yellow arrow, is an asteroid, even though on the picture it looks exactly like a star, there's no way you could tell from this single picture that that object designated by the yellow arrow is in fact an asteroid, part of our solar system, not part of a distant plethora of stars out at great distances from us. The only way you could tell the difference would be to take another picture. So here's another picture. These are real pictures, by the way. And this picture was taken 3 hours later. the same telescope pointed in the same direction towards the same field of stars. And as you can see, the object at the end of the yellow arrow has changed position. Every other object in this field of view is the same, because every other object in this field of view is a distant star, tens of light years, hundreds of light years, thousands of light years away. But that one object, that one little dot has changed its position, which tells us that that one little dot is something that's nearby, astronomically speaking, something moving around the sun, an asteroid. Incidentally, when you look at a picture like this of a field of stars, you notice that some of the stars appear bigger than others. And the asteroid appears about the same size as the average star in this picture. Just a great point about looking at pictures of fields of stars. The size of the little dots that you see for the stars, the size recorded by the electronic or a regular camera that was used, the sizes of these dots bear no connection whatever to the physical sizes of the stars. Because the stars, the true stars out beyond our solar system, the true stars are so far away that they're all little points of light, tiny little points of light. They're so far away. But when a picture is taken of a group of stars, the brighter stars create a bigger dot in the picture. Because when the light from a brighter star strikes the camera, it spreads out a little bit. So the larger dots that you see here are not necessarily bigger stars. They're just brighter stars. In any case, that's how we know that we see an asteroid in this field of view, because the asteroid has moved and all the other objects in the frame have not. And that's how asteroids are discovered. That's how they've been discovered for now well more than a century. Photography is crucial to the discovery of asteroids because you have to detect an object in the sky that looks just like a star in your picture, but it's different in the sense that it moves slightly and wanders. It shifts its position over periods of hours. And you can see in this particular case, this particular asteroid has the name Pallas. It's one of the larger known asteroids. Its position has clearly changed in this picture in just 3 hours. So it is an asteroid. Now, if you discover an asteroid using this technique, taking two pictures of the same field of view in the sky, but the two pictures are separated in time by maybe a few hours, or in some cases a day or two. If you do this, then you can begin to record the motion of the asteroid against the background field of stars. And if you study the motion of an asteroid against the background field of stars over a period of time, maybe a few weeks, maybe a few months or longer, then that information can be used to construct the orbit of the asteroid around the sun. And the longer the time frame that you have to study the motion of this asteroid, in other words, 1 month is better than 1 week, 1 year is better than 1 month, the longer you have to study the motion of an asteroid against the background of stars, the more accurately you can calculate the orbit. And that's important, especially it's important when you think about asteroids that might possibly be in an orbit that takes them close to the Earth. If you really wish to know the orbit of an asteroid in great detail with huge accuracy, you need to observe the motion of that asteroid against the background of stars over a considerable period of time. So here now is an example of an asteroid orbit. In fact, this asteroid is the one that's in some sense the subject of tonight's talk. The asteroid has a somewhat poetic name, 2024 YR4. Now, I did graciously offer to have my name associated with this asteroid. It didn't really take off. Of course, that's not the first time that the naming of an astronomical object didn't really take off. A little side story here, but in the late 1700s, a British astronomer named William Herschel, for the first time in history, discovered a new planet in the solar system, the planet being Uranus. And having discovered it, he decided he would name it. He's a British guy. This was during the American Revolution, it turns out. Anyway, William Herschel wanted to name that planet, which today we call Uranus, he wanted to name it George's star, as in King George. That son of a gun, King George, of course, was the king of England during the time of the American Revolution. Didn't work out. Anyway, so much for naming things. Here you see an example of an asteroid's orbit. Now in this diagram, you see the sun at the center, and then sort of a purple color is the orbit of Mercury, and then you have the orbit in this diagram also of Venus and Earth. and out to Mars. The Mars orbit is in sort of a red or orange color, and just bits and pieces of the orbit of Jupiter are seen along the edges of this image. And so that is the orbit of this asteroid that's of been recent concern and has been publicized and discussed in the press for the last few months. That's an example of the orbit of an asteroid, and to determine that orbit, one has to observe the motion of the asteroid against the background of stars over as long a time as possible, and then use various types of calculations, making use of Isaac Newton's principles of motion and gravitation to figure out what the orbit is. So now this has been done for a long time. It's been more than a century that astronomers have had the ability to discover a fair number of asteroids. And so here you see a diagram generated by computer of the positions of a large number of asteroids on August 14th, 2006. You see, if you know the orbit of an asteroid, if you have a big database with the orbital parameters, the orbital constants of asteroids, then you can use that information in modern times with modern computers. You can use that information to determine where the asteroid will be, more or less at least, at any given time. So a big database was data crunched by a big computer, and all the orbits of these known asteroids were calculated, and it was figured out on that basis where they all would be on that particular date, which has no particular significance, that date, as opposed to some other date. But the white dots there represent individual asteroids. And if you look carefully at this diagram, you can see that most of the asteroids in our solar system, most of this construction debris lies between the orbits of Mars and Jupiter. And that region in our solar system between the orbits of Mars and Jupiter is known as, oddly enough, the asteroid belt. But not all of the asteroids lie in the asteroid belt. Not all of the asteroids lie between the orbits of Mars and Jupiter. Some of them come in closer to the sun. Some of them come in to distances from the sun comparable to the distance of the Earth from the sun. And those are the ones we worry about. Now, there are some other types of asteroids shown here in green. The colors, of course, are strictly arbitrary. There are some other types of asteroids, other orbits, one called Greeks, the Trojans, the Hildas. These are asteroids that are out at about the same distance from the sun as Jupiter, and which are significantly affected gravitationally by Jupiter's gravitation. Jupiter, of course, the most massive planet in the solar system, has a significant gravitational effect on objects roughly near it. So most of the asteroids are out there in the asteroid belt. We don't care about them in some sense because they don't bother us. They're not going to strike the Earth, but there are some which are a little bit closer. So let's take a look at what asteroids look like, at least a few of them, just briefly. You see, for most of astronomical history, even after asteroids were first discovered in the early 19th century, for most of time in astronomy, asteroids were just little bits of light in the telescope eyepiece or on a piece of film or an electronic image. As seen from Earth, asteroids, they're just little tiny bits of light. They look like stars, as I said, except they move slowly against the background of stars. In order to understand what asteroids really look like up close and personal, you have to get up close and personal. And so here you see two pictures, one, of course, on the right, obviously the moon, and the one on the left shows the largest known asteroid, and probably the largest asteroid, because if there were any bigger, we would have found them by now. This asteroid is called Vesta. Vesta is about 300 miles across. So it's obviously a lot smaller than the moon. I just put these two together on the same slide to show the relative sizes. One thing you'll notice when you look at Vesta is that unlike the moon, Vesta is not really round, it's somewhat elongated. And the reason for that is that large objects in the solar system, and large objects in the universe at large in many cases, large objects in the solar system have enough gravity so they pull themselves into a spherical shape. That's why the Earth is round, because the Earth has enough mass inside it, and hence enough gravity to pull itself into a spherical shape to try to get all the stuff as close as possible together. So larger objects in the solar system are invariably spherical, or at least approximately spherical. But smaller objects, such as, for example, this asteroid and all the other asteroids, they're small enough so they don't have enough mass to pull themselves together into a spherical shape. So asteroids in general, unlike the moon or the Earth or other planets or most satellites in our solar system, asteroids generally have irregular shapes. They just don't have enough gravity to pull themselves together into a sphere. You can see that there. Here's now another image. This image was taken by the Dawn spacecraft. All these images of a few asteroids that I'm going to show you, all of these images were made by spacecraft that ventured very close to the asteroids. As I say, the asteroids themselves, as seen from Earth through a telescope, are just little points of light. But when you get out into the solar system, human beings, you see, are very clever people, not so much me, but human beings, some of them at least, are very clever people. And they figured out how to design, launch, and control spacecraft to go out there and take these pictures. You see the outline of Kentucky there to give you a sense of scale. And you see quite a few craters on the surface of this asteroid. Asteroid is probably mostly made of solid rock, pretty solid in any case. It's been pockmarked by smaller objects that have collided with it. And at the very bottom here, it's not so obvious when you look at it, but at the very bottom of this slide, right above the name Dawn spacecraft, is a mountain on this asteroid Vesta, and that mountain is twice as tall as Mount Everest. It turns out that if an object is smaller and has less gravity, then it can, under suitable circumstances, have pretty tall mountains. It wouldn't be possible with the Earth, given the Earth's much stronger force of gravity. So here you see it. And here's now another image also from the same spacecraft that shows just another view of Vesta, which again, as I say, is about 300 miles across and is the largest asteroid. This is an interesting image because there's sort of a circular, almost bullseye pattern there, and no one knows exactly what caused that. It might have been the result of an impact long ago involving Vesta and an object of relatively similar size to Vesta. Or maybe something was going on in the interior of Vesta billions of years ago that created that. We don't know. Now, when you think of Vesta, and when you're in Kentucky, of course, you think of basketball. Because everything in Kentucky is either related to basketball or bourbon or horses. That's the way it is. Sometimes a bit of football, but anyway, I just did a simple calculation some time ago. As you can imagine, Vesta being much smaller in size than the Earth, the force of gravity at the surface of the Earth is much stronger than the force of gravity at the surface of Vesta. That is to say, if you stood on Vesta, you would weigh much less. In fact, the force of gravity on the surface of Vesta is 1/40th as strong as it is at the surface of the Earth. So, for example, if you weighed 120 pounds, well, let's say 80 pounds. If you weigh 80 pounds, and a younger person weighing 80 pounds here on Earth, you would weigh just 2 pounds on Vesta. What that means for basketball is you could jump much higher. How much higher? It's a simple calculation. I won't go through it. But let's just say a basketball player here on the Earth can jump up 10 feet. I'm sure there are some who can do better than that. But anyway, if you can jump 10 feet here on the Earth, now you go to Vesta, and now you jump under its gravity, which is so much weaker. And now you could jump 166 feet. Imagine that. Imagine a basketball game. Imagine a basketball game where when the player jumps, he or she goes up 160 or so feet to dunk that ball. That would be an interesting play because given the gravity that's so weak on the surface of Vesta, if you jump up, it would take you 20 seconds to get up to the top of the basket there, and then another 20 seconds to fall back down. So you think about it, you could actually almost have a commercial break with each basket. Because it would take 20 seconds up, 20 seconds down, that's 40 seconds. You could work it easily. It'd be perfect for TV. The one problem is there's no air to breathe there. So you would be dead, which would make it difficult to
shot
jump.
clock would run out on the way up.
Sorry?
The shot clock would run out.
The shot clock would run out on the way up. That's a good point. Well, that's actually, you'd have to have a different shot clock. I'll get it. Yes, they'd have to have a different clock. That's right. That'd be an issue. Okay. So let's just look at a few more asteroids before we get down to business with the asteroid at hand. There is now a picture in the upper right. You see Vesta, and you see some other smaller asteroids that are kind of hard to see in the picture. But if we just look at those smaller asteroids, the smaller asteroids are shown in the same size scale as Vesta. Vesta, as I said, is the largest asteroid known. So there are many, of course, by definition, smaller. So let's just look now at those asteroids that are a lot smaller than Vesta. Here they're shown now in greater detail. All of these images, then, as I've said, come from spacecraft that have passed by these asteroids. Until recently, until just a few decades ago, we had no idea what the shapes of asteroids were. Only when spacecraft passed by, or in some cases, orbit, do we get close-up pictures and know what they're like. So here you see the names of these asteroids come from wherever, but you can see they have different shapes. They're not round, even more out of round than Vesta. They just look like little chips of rock or other material. They're so small, as I said, even Vesta is small enough to not have enough gravity to be spherical, Vesta, but these are even smaller. So they're not round. They're all kinds of shapes. Here's another one, also seen by a spacecraft called Lucy. Anyone here named Lucy, or with the sound of my voice, well, you have a spacecraft named asteroid named after you. And Lucy is even better than a regular asteroid because Lucy has a friend. Lucy has a satellite, and you see that in the lower right. And the football field that you see in this diagram is designed to show you a sense of scale. So this asteroid is a lot smaller than the 300-mile across asteroid Vesta. This asteroid is just maybe 1,000 feet across or something like that. And other asteroids are much smaller, by the way. Here's one now. Let's get down to brass tacks here and talk about near Earth asteroids. Near Earth asteroids represent a small fraction of the total number of asteroids. As I said, most asteroids in our solar system lie between the orbits of Mars and Jupiter, but there are some that venture in closer to the sun. And one of them is called Apophis. Apophis. This could be something you could worry about if you wanted to. I don't really want to worry, I won't, but this particular asteroid is known as a near Earth asteroid, or an NEA, because it, as the name suggests, does venture fairly close to the Earth at times. And here you see a diagram. The outer circle that you see there, or near circle, is the orbit of the moon. And you see the trace of the projected trajectory of that asteroid, Apophis. What day? Friday the 13th. On Friday the 13th, in 2029, forget about 2032, which is the time when this other asteroid that I'll talk about later is supposed to come close to the Earth. We know that in 2029, an asteroid that is more than 1,000 feet across, that's something that could do serious damage to the Earth, not to the Earth as a whole, but to civilization. This asteroid in 2029, on Friday the 13th, April 13th, 2029, will pass very close to the Earth. It turns out, though, we know the orbit of that asteroid so precisely that we know it will not strike the Earth, but it will come very close. A close shave. In fact, it will come to within about 2.5 Earth diameters to the surface of the Earth. But that's close and no cigar, as they say. Fortunately, we'll be safe. But it may be something that will be visible to the naked eye. I plan to try to see it a few years down the road. Apophis. Happy Friday the 13th. But anyway, let's talk about another asteroid that's of no danger to us, but is of interest because it's been visited very closely by a spacecraft called Osiris. This asteroid is called asteroid Bennu. I don't know where that name came from. I guess it's someone's name. This asteroid orbits around the sun at about the same distance from the sun as the Earth. As you see here, it's about 0.3 of a mile in diameter. I'll show you pictures of it. This asteroid is of particular interest because it was visited by this spacecraft, Osiris, a few years ago. In fact, a sample from this asteroid was actually collected by this spacecraft that landed on the surface, touched down, and then pulled back with a sample of that asteroid and returned it to Earth. Returned it to Earth on September 24th, 2023. So let me show you a few pictures here. I like these pictures because it's just amazing to me that human beings can design and operate machines, devices that can take pictures like this. They're robotic spacecraft sent out into the solar system to inspect various objects orbiting around the sun, planets, asteroids, and so forth. This picture taken in 2018. The football field, again, gives you a sense of scale. This is not a large asteroid compared to, say, Vesta, but if something like this ever struck the Earth, there would be, as the expression goes, hell to pay. What Vesta actually is a big pile of junk. You know, one thing they have at construction sites sometimes, and maybe across the way there from this building, one thing they have at construction sites are piles of junk, stuff that's the result of whatever they're doing. Well, this asteroid is just a pile of junk, very loosely held together by its very weak gravity. Here's another image of it. It has a somewhat irregular shape. You can see some indications of small craters there. The football field again gives you a sense of scale. And here's now a symbol of the Empire State Building, to give you also a sense of scale. But we can get much closer to this asteroid than I've shown you so far. This is already very close. We're looking now at construction debris. You might say, well, if it's construction debris, who gives a darn about it? Well, the reason why astronomers are interested in asteroids, and in particular, the reason why they were interested in returning a sample of this asteroid, or for that matter, any other, but it was done for this one. The reason why astronomers are interested in studying asteroids is because asteroids are made up of material that was around when the solar system was formed. Asteroids are almost like a history book, if properly read, if properly understood. They tell us something about the early conditions which gave rise to our solar system. They tell us something about our origins, and astronomy, among other things, is the science of origins. Not only how things are today in the universe, but how they got that way, especially here in the solar system where we live. Here's now a picture that shows this spacecraft approaching very closely the surface of this pile of rubble that is an asteroid. Now I have to use the basketball court to give you a sense of scale. It's just a bunch of rocks. When I think of a bunch of rocks, these are very interesting rocks. I'm reminded of a story my dad told many, many years ago. He's been gone for some time, as you can imagine, someone of my age, but many, many years ago, he was living and working in the Middle East. And he took a vacation opportunity to go visit Athens. And he was walking up a rather steep hill to the Acropolis of Athens to see the Parthenon. And as he was walking up on this somewhat warm, maybe hot summer day, he passed an American couple. And just as he passed them, the woman said he was going no further. She said, I'm not walking another step up to see a damn pile of rocks. That being, of course, the Parthenon. Well, I would walk some distance to see this damn pile of rocks, because this pile of rocks tells us about conditions in the early solar system, conditions that ultimately led, well, to us. Let's zoom in a bit more. If you look carefully, you'll see the small icon of a human being that, again, give you a sense of scale. So you're just looking at a bunch of darn rocks, but they're very interesting rocks. Maybe more interesting than the rocks that make the Parthenon, depending on your perspective. And one other picture. Now that somewhat squarish white rock that you see there along the edge of a crater, that somewhat squarish white rock there, for a sense of scale, is about the size of a passenger van. So we're quite close. You see the 100-foot double arrow there. We're very close now to the surface. Let's go down and get some. This is now, of course, an illustration that shows how this spacecraft actually maneuvered itself down to the surface of this asteroid. And it had a sampling arm, which you see there about to strike the surface, which was designed to grab some material and just jump right off. Let's look. This is an actual picture made by a camera on the spacecraft as it was about to grab that sample of the asteroid. You see the sampling arm there. It's just about to touch that pile of debris. It's just about to touch, and now, bingo, it is touched. Because the gravity is so weak, everything is thrown up in the air. There's no air, really, for it to be thrown up into, but thrown up in any case. And now, one more. And now, some years later, on the preordained date of September 24th, 2023, a capsule from that spacecraft landed in the Utah desert, and it contained samples of this asteroid. And here is now an image in the laboratory that shows part of the sampling container, and some of the material sort of spill out. You can see it there at the end of the yellow arrow. What you see there just looks like a bunch of coal or otherwise very uninteresting rocks. But what you see there is a sample of material that goes back to the very earliest times in the history of our solar system, a sample of that asteroid, a sample of that piece of construction debris, which can tell us much about the early history of our solar system, which gave rise to us. Here's another asteroid also taken by an image made by a passing spacecraft, in this case, a Japanese spacecraft. The Japanese have been very active in space exploration for a long time. And again, you see that these don't look round at all. They are so small, they don't have enough gravity to pull themselves together. Now, I remember showing this picture. I remember showing this picture in one of my astronomy classes, a year or two ago. There it is. Same thing. You see the football field for size scale. I showed this picture and someone said it looked like a chicken nugget. So let's see what you think. There's a chicken nugget. And somebody else said, no, it looked more like a baked potato or maybe an unbaked potato. There you see that. You can make your own judgment as to what you think this particular asteroid looks more like, or maybe neither. So now we get to the heart of the matter. The heart of the matter. The asteroid, the Near Earth Asteroid, about which most of you have heard in the last few weeks, or maybe several months, really. An asteroid that was only discovered in late December of this past year. And it was discovered by a telescope system in Chile, which is designed to look for asteroids by taking pictures of the sky over different periods of time and comparing them to look for something that's moving against the background of stars. And this is one of the asteroids they found. And after observing the motion of this asteroid against the background of stars for a few weeks, they were able to calculate the orbit, at least the approximate orbit. And that's what's shown right here. You see in this diagram, you see the sun at the center. Of course, the sizes of these objects are not the scale. You see the sun at the center. The white circle is the orbit of Mercury. The yellow circle is the orbit of Venus, and the blue circle is the orbit of the Earth. The red circle is the orbit of Mars. Excuse me, the red circle is the orbit of the Earth. I'll get it right. When I think of Mars, I think of stuff that's red. Anyway, the red circle is the Earth's orbit. And of course, you see then the orbit, the calculated orbit of this asteroid that's been so much in the press lately, 2024, YR4. And you can see now, that asteroid has a somewhat elongated orbit. It's not as nearly circular as the orbits of the planets. The orbits of the planets are not, strictly speaking, circular, but they're fairly close. This asteroid has a somewhat more elongated orbit, which takes it at different distances from the sun over time. But you see, this is the calculated orbit between the time of October 2028, looking into the future, and 2036 after the encounter. So here you see it. If it starts one more time, we'll see this again. It starts one more time. And there we go. Up it goes, up it goes. 2030, 2031, coming into 2032 around. It's going to hit the red circle. Boom. The buoy, maybe. And so this is the object that astronomers became worried about, because when they calculated the orbit, although there were always uncertainties in calculating these orbits, it looked like the orbit had some decent chance of striking the Earth. But as time went on, after the discovery in December, and they were able to observe the motion of this asteroid over a longer period of time, they were able to refine the calculation of the orbits. And now it appears as though, well, I shouldn't tell you. I don't want to give it away. So here's some information about this asteroid. It was discovered, as you see, in late December of this past year. So it's only been known for a few months. It's not surprising. Asteroids are discovered all the time. It's estimated to be a few hundred feet across. So it is not a huge civilization killing size asteroid miles across, but you know, if this asteroid struck if it struck Lexington, it would be a bit of a mess. It orbits around the sun every 4 years, and now we know from calculations of its orbit, when it comes close to the Earth on Christmas Day, this last Christmas, while you and I and others were either celebrating Christmas or whatever holidays you celebrate around that time, when that was happening here, this asteroid made a close approach to the Earth. Now, close was not that close, December 25th, 2024, it made a close approach to the Earth. At its closest, it was twice the Earth-Moon distance. Now, the Moon is pretty far away from the Earth. The Moon is 30 Earth diameters away from the Earth. So the Moon is pretty far away. And at this closest approach, which no one knew about because this closest approach we now know occurred 2 days before the asteroid was discovered. This close approach was twice as far away from the Earth as the Moon. Pretty safe, very safe. But now, 4 years later, in December of 2028, it's going to make another close approach to the Earth, this time further away, though, about 20 Earth-Moon distances away. That's plenty of safety. But then December 22, 2032, another 4 years later, that's the issue. That's the issue. Will there be a Kablawi or not? Well, it turns out no. You probably know this. Most people here perhaps read in the press that more recent calculations based on further refinements of the orbit of this asteroid. The further refinements possible because the asteroid has now been observed moving against the background of stars for a longer period of time, which allows for a more accurate calculation of the orbit. Now we know that there's only about one chance in 1.8 million that the asteroid will strike the Earth. That's pretty good odds. That's a whole lot better odds than, let's say, Russian roulette, 1 in 1.8 million. Not bad, not bad. And when the asteroid makes its relatively close approach to the Earth in 2028, not that close, but somewhat close, the next close approach in 2028 will pose absolutely no danger to the Earth, but it will allow astronomers to carefully observe the motion of the asteroid again and to even further refine the orbit, the accuracy of the orbit calculations. And so what will surely happen is that after the observations around December of 2028, during that close passage, after those observations are made and further refinements occur, then the odds will become even better. But I'll take 1 in 1.8 million. That's fine for me. I'm an old guy, so maybe I'm willing to take more risks. No, but 1 in 1.8 million is not bad. Now you might ask, how often do asteroids of this size strike the Earth? Is this something that only happens every now and then, or just then, or hopefully not now? Turns out statistically, asteroids of about this size, a few hundred feet across, strike the Earth once every maybe 10,000 years. So the chances that an asteroid like this are going to strike the Earth at a time of anyone in this room is alive, or anyone hearing my voice elsewhere, your chances of going to your demise as a result of an asteroid strike like this that occurs on the average once every 10,000 years, those chances aren't very high. But here's an interesting fact. From what we know of the asteroid orbit now, from what we know, there is a much better, although not particularly great chance that the asteroid will strike the Moon. This asteroid, which is almost certainly not going to strike the Earth in 2032. In 2032, it has a 1 chance in 60, according to the current orbit calculations. This asteroid has a 1 chance in 60 of striking the Moon. And that would be very interesting, actually. It wouldn't, of course, hurt us, but it would be interesting to see what happened to the surface of the Moon as a result of that. It wouldn't create a huge effect on the surface of the Moon. The indications are it would probably, if it were to strike the Moon, it would create a crater that might be a mile or so across. So we'll see. Actually, astronomers now relieved that that the chances of the asteroid striking the Earth are virtually zero, are now become excited that the asteroid might strike the Moon. But even that chance is not very high. And as the calculation of the orbit becomes more and more refined in the future, especially after that next close passage in 2028, then the chances are we'll know with even greater certainty whether or not, most likely not, the asteroid will strike the Moon. So here is now a little table, not that these are numbers that you can commit to memory, but based on statistics and estimates, this is a table which indicates how often asteroids strike the Earth. And the answer is the smaller ones strike far more commonly than the larger ones, for the simple reason that smaller asteroids, even going down to those a few feet across. Smaller asteroids are far, 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 far more common than the bigger asteroids. So statistically, our chance of being struck by a large asteroid, those chances are very small, even though the potential danger would be very high. As you can see, asteroids 3 feet across, roughly, we think enter the Earth's upper atmosphere a few times per day. They never make it to the ground. They're simply vaporized on their way into the atmosphere, create a bright meteor in the sky or shooting star, but that's about all. 30 feet across, maybe once per year, that would create some kind of atmospheric explosion. Not serious, not dangerous. No big deal, but an interesting phenomenon in the sky if you got to see it. 300 feet across. I put that option in red because that's roughly the size of the asteroid I've just been talking about that is going to make a close path by the Earth in 2032. And so an object like that, as I said earlier, that a few hundred feet across, typically, statistically, will strike the Earth once in maybe 10,000 years. And even so, a object 300 feet across would probably not create a crater on the Earth. Most likely, such an object entering the Earth's atmosphere would burst under the stress of passing through the atmosphere and being heated and slowed down, burst into a whole rain of material, some of which might fall on the ground, which would create a shock wave, which might blow down trees or buildings. That wouldn't be a good thing, the 300-foot object striking the Earth, but it wouldn't be disastrous to civilization. 3,000 feet once per million years, that causes a crater, especially if it lands on the land. But of course, something striking the Earth is really more likely to hit the ocean, since the ocean covers a larger fraction of the Earth's surface. And now 6 miles, that's a pretty big object. Now, it's small compared to the Earth, of course, but a 6 mile object striking the Earth will create to use a technical term, huge mess. And that is what we think happened, and I'm sure many of you know about this. 65 million years ago, an asteroid, or possibly a comet nucleus, we don't know for sure, some few miles across, something that happens only typically once every few 100 million years, 6 miles across, struck the Earth in the vicinity of today's, as we call it, Yucatan Peninsula. Oops, one back. Anyway, let's see. Let's go back. Yes. 6 miles big, 6 miles in size. That's a good size. And that created a global climate catastrophe. And as I'm sure most, if not everyone knows, that global climate catastrophe that was produced by this impact 65 million years ago of an object a few miles, like maybe 5 or 6 miles across. That impact disrupted the entire ecosystem of the Earth, led to the demise of most dinosaurs, except the avian dinosaurs, which today their descendants are birds. And biologists have speculated that this global biological cataclysm produced by the 6 or so mile wide diameter asteroid striking what's today called the Yucatan Peninsula, that cataclysm, having destroyed most of the dinosaurs, opened up an ecological niche for mammals, which already existed at that time, to develop further and further, leading up to us. So the fact that we are here in this room, the fact that Homo sapiens, human beings, have evolved to a point where they have, may be a direct outcome of an asteroid impact 65 million years ago, an asteroid that was a few miles across.
Yeah.
We wouldn't be here perhaps otherwise. We would be still ruled maybe by dinosaurs. Who knows? Now, one last slide before we end here. I will be happy to take questions, but you might say, what about the future? What about the future of asteroid discoveries? And the answer is, the future of asteroid discoveries is that we are going to be discovering more and more and more and more and more and more of them. Not that there will be more and more and more and more of them, but we will be discovering more and more of them. And this observatory, which is on the verge of opening, it's been under construction for years and planned for decades. This observatory is called the Vera C. Rubin Observatory. It is in the Chilean Andes, and it will begin operation if all goes well this year. It has a very large a mirror that's 27 feet across, this huge curved mirror to collect light from faint objects in the universe. Some of the faint objects that this telescope will study are objects that are billions of light years away, but it also will be able to see faint objects that are much nearer to us, namely asteroids. And in particular, this facility will be very good for studying asteroids, as well as many other scientific goals of astronomers. But anyway, thinking of asteroids, this observatory has the telescope has a very wide field of view. So in just a few days' time, you can take pictures of every direction in the sky that's above the horizon. And then it can go back 4 days later and do that again, and go back 4 days later and do that again. And then compare all these images and look, among other things, for objects that have changed their position in the sky. And those objects will in general be asteroids. And the prediction is that the Vera C. Rubin Observatory, named after a very prominent woman who was an astronomer and passed away a few years ago, that this observatory will discover millions of new asteroids. So what's going to happen in the future is we're going to get more and more of these asteroid alerts, not because there are more asteroids out there or because interplanetary space is any more dangerous than it used to be, but we have the ability now to detect many, many, many more asteroids, or we will have once this telescope is operational, the ability to detect many more asteroids than we ever had in the past. Millions of them. There are millions of them out there. We know that. Most of them are pretty small, but even a relatively small asteroid can be bad news for the Earth. So this will be a very important observatory for asteroid detection, and also for many other topics of interest to astronomers that go on far beyond the distances to asteroids. So that's all I have, folks. I am open to questions, of course. Perhaps all of you now feel that you're safe. You need not worry about the upcoming December 22, 2032 close encounter with an asteroid. You're safe. There's so many other things to worry about. Thank you very much. Yeah. I would be happy to answer questions that people have. I also realize that many people here have other things they may need to do. So if you at this point feel you need to leave, by all means, feel free to do that. Anyone who's interested in sticking around for a few minutes is welcome to do so. As I say, is you're welcome to go about your evening as well. I'll take my questions. Yes.
I just want to make a quick comment. I really like your slide that showed the asteroid material brought back to Earth.
Yes.
Because what you don't realize when an asteroid has a picture taken of it is how dark it is.
Yes. Yes.
Even the close-up spacecrafts try to correctly expose it
Yes.
to a grayscale or whatever, okay? But you don't realize that really those things are actually almost coal black. We've shown very well on that slide.
Yes.
I'm glad you showed that slide.
Most asteroids are mostly very, very dark. They reflect very little light. You know, if you had some asteroid material, here's what I was thinking, actually. I'm not that honest at first, frankly. And I was thinking of getting some coal and just grinding it up and then selling it to people for a large amount of money as asteroid material. Now, I know you folks are you'd be too smart to go for that scale. I could work that with you, but maybe there's someone here, maybe not. I don't know. I think I'd just sell it to myself. But that's right. Asteroid material looks a lot like coal. So, but as I say, it is material that tells us about the early history of the solar system.
So we have a posse over the telescope.
Sorry?
Does she have a posse over?
Yes, for those who may wish to go over to the telescope, as you I'm sure know, many of you know, we have a very nice astronomical telescope on the top of the parking structure just across the way from the facility. And Erica will be going over there. And if you do wish to stick around and take a look, one thing I can tell you is that the full moon will be up because the eclipse of the moon occurring in the early morning hours of tomorrow morning only occurs when the moon is full. Yes, sir.
So how does the dust transport rocks if there's no gravity to compress it?
Well, there's not much. There's enough. These asteroids, especially the smaller ones made of loose material, are just barely held together by their own gravity.
But how do they compress rock? Like how do they compress?
I mean, how do they form?
Rocks? Like why doesn't it just stay as rocks? Why is it big rocks?
Probably because they are fragments of much larger bodies than themselves, and then we're broken up by collisions early in the history of the solar system. That's the question. Anything else?
Any more questions?
Do we have a contingent from Lexington Catholic here? Okay, good, very good. Always a pleasure to see young people from, Lexington Catholic who, come here. Their teacher encourages them to come here and hear these talks. And other people in the audience as well, glad to have anyone who's interested in astronomy, and we have these lectures, as I've said, and as you see there on the slide, on the second Thursday of each month. I'm not certain about the summer, at this point, but there will be a talk in April, very interesting talk. One of our most recently, in fact, our most recently hired astronomer, Ryan Sanders, will be talking about the James Webb Space Telescope and uses it for his own research. Another one of our recent hires, Manwat Su, will be talking about how to bake a universe. What she's really talking about is how did the universe come into being? The universe was very hot early on, so it got baked. And these talks, I'm sure, will be quite interesting. So think of those, consider those if you're free on those days.
The next talk might be an emeritus talk.
That's true for me, yeah, that's true. I'm going to be retiring at the end of the semester. Well, I still might be